Good. How are you?
Well. Okay, cool. We're all set.
Maybe I use it for the introduction. And I give it to you.
Sure. Yeah.
We can wait a few more minutes.
Okay, no problem. No, I had enough food.
I have to leave at 4:30
Oh,
exactly.
no worry, no worry. Yeah.
I'll send you an email after.
Okay, okay, sounds great. Well, the most important stuff is going to be on the second part.
Okay, so good afternoon, everyone. And thank you all for being here. First day of semester. You're very brave. So it's my great pleasure to introduce our first speaker of the semester, Yongxin Chen from Georgia Tech. Let me give you a brief bio of Yongxin. So he's currently an associate professor in the School of Aerospace Engineering and the Center of Machine Learning at Georgia Tech. So, and before that, he was a faculty member at Iowa State University from 2017 till 18. So Yongxin did his bachelor in Shanghai Jiaotong University in 2011 and PhD University of Minnesota, both in mechanical engineering. So Yongxin has received many prestigious awards, which I only mention some of them in Control System Society, including Axelby Award in 2017, Ekman Award in 2022. Of course, on top of that, he received also NSF Career and other Young Investigator Awards as well. So today he's going to talk about safety assurance of stochastic systems. And so there are some logistical issues, I guess. Okay, so let's thank Yongxin for being here today, and floor is yours.
Hello? Hello, can you hear me? Okay, thanks a lot for the introduction and for the invitation. It's a great pleasure to be here, and thanks all for coming. I just got to know it's the first day of the semester. I know how difficult it is to attend an event like this. Okay, so today I would like to share some recent work from our group on the safety of stochastic system. It's something we are very excited about. And yeah, and feel free to ask me if you have any question, just stop me, okay? And this is the joint work with SIBR, actually it's a CU Boulder, and two of my PhD students. So we started this line of research a few years ago. It all started with, I was sitting in a very beautiful talk given by SIBR. So he was talking about the reachability analysis. Then I asked the question is, how do we do this for stochastic system? Then all of this work just come out, okay? So not automatically, but yeah. So today I'm going to cover mainly two papers we have recently, and both of them, they have been published, I think, at Tech. And okay, let's get to the topic. So we are interested in safety critical applications. So safety is essential in almost all the engineering systems, especially those who involve human in the loop, right? For instance, if you are sitting in a Waymo AV, you want to make sure it's relatively safe. Right? If the accident happened very often, you would choose not to use the service, right? And many other services like a surgical robot, right? You want to make this sure they're safe. So there are many systems. Almost anything involve human in the loop, they have to be safe. So these are safety critical applications. So how do we ensure a system is safe? There have been a lot of work, research, and also engineering going on in this area. So inside the control community, we have several popular tools that can ensure the safety of dynamic systems. So these are the two most popular ones, I think. And the first one is called the barrier function, okay? The idea is very simple. So what you want to do using the barrier function is you want to make sure the safe set is what they call the forward invariant. Basically, it's forward invariant means if you start from the safe set, you're going to stay in the safe set forever, right? That's automatically can guarantee safety. And another one is reachability analysis. It's very different. So in reachability analysis, is basically if every possible future is safe, then for sure you are safe. So in reachability analysis, basically what they are doing is you are trying to approximate the ensemble of other possible futures and then say this is safe, then the system is safe. So these are the two most popular paradigms in control community trying for the safety verification. Okay, so there still are many challenges in safe autonomous systems. So here, there are many actually pages of challenges. So it's still open problems. We are not claiming we solved the problem, but we made some progress in this direction. So there are many challenges. So here, the challenges we are focusing on are these three. So high-dimensional dynamic systems, okay? So for instance, when you have a humanoid robot, the number of states could be 20 or 30, or for power systems is even higher. So we are talking about high-dimensional system. So high-dimensional system, typically some traditional method based on discretization would face what they call curse of dimensionality. So computation is going to be a bottleneck. Then another thing is the dynamics typically is complicated, it's nonlinear. So if you have a linear system, things become much simpler. But if you have a nonlinear system, then it's very difficult to capture the future trajectory. So that's another complexity. And another one, of course, is the uncertainty. There is no system in real world that can operate without uncertainty. There's always uncertainty. It's just a matter of scale, whether it's large or small. And if you want to ensure safety, you have to account for this uncertainty. Otherwise, it's not safe, okay? So these are the three challenges we would focus on. Okay, let's look at this. So we would consider two types of uncertainties, okay? So one type of uncertainty is called the deterministic uncertainty. So deterministic uncertainty typically is bounded, and other than that, you don't know anything about it. And usually for deterministic uncertainty, what you care about is what they call worst case performance. You want to make sure in the worst case scenario, you are safe. So this is something widely used. This is the uncertainty model used in robust control, which is a branch of control. Another type of uncertainty we care about is the stochastic uncertainty. Stochastic uncertainty is quite different. So typically it's unbounded, like a Gaussian noise. But the good thing is you know the statistics. You know, oh, this is random, and every time point, the disturbances are independent from each other. There's something you know, the statistics. And typically in this type of uncertainty, what you care about is in average. You want to make sure in average is good, right? It's not the worst case. Because it's unbounded, whenever you ask about the worst case, there's nothing reasonable, okay? So this is the uncertainty model used in stochastic control, okay? So this is our goal. This is our goal, and also our problem formulation. We would like to develop a scalable and effective algorithm to, let's say, verify the safety of a general nonlinear dynamic system under both deterministic and stochastic uncertainty. So if you want some formulas, so this is what we consider. So the first one is a continuous time system. The second one is a discrete-time system. So let's look at the discrete-time system. X is the state, dt is the deterministic disturbance, which assume it's bounded. Then Wt is the stochastic disturbance. We can assume it's Gaussian or sub-Gaussian. There's some assumption on it. And we assume we know the model. And we want to verify the safety of this system. This is the continuous time version, but you can just view this as a Gaussian noise. So this is, after you discretize this, you get this, okay? So it's just a language. So don't worry too much. It's more or less a differential equation driven by white noise. Okay, so we would like to verify the safety for this type of system when the state dimension is huge, when this F can be general nonlinear system, and we want to make sure that we can do this in real time, okay, very fast. Okay, so that's the goal, okay? And due to the constraint of time, I'm going to focus only on the first one, but everything we talk about can be equally applied to the discrete time system. So there's no barrier between these two, okay? So this is the problem formulation, the setup. So how do we do this? We adopt approach which based on reachability analysis. So you predict all the possible future and make sure the possible future are safe. Then your system is safe. But because we have a stochastic system, we have to do some modification. So this is the outline of the rest of the talk. I'm going to talk about two things. The first one is the reachability analysis for stochastic system. And the second one is safety verification. So how do you modify the reachability analysis for stochastic system for real safety verification? Okay, there's a small gap there, but I'm going to start with the first one. It's easier, okay? So let's start with the first one. So I'm going to give a quick review of the reachability analysis. So what is the reachable set? It's approximation of all the possible future. So in the more rigorous language, so this is what you do. You have some dynamic system, which let's say your car, okay, which you have certain state, and you are driven by some disturbance, which you assume is bounded somehow. And you have some initial state, but there may not be a fixed value, but you know roughly where it starts. The deterministic reachable set is basically all the possible value xt if the system starts from this initial set and the disturbance belongs to this bounded set. Okay, so it's basically the set of all the possible future at that time instance. Okay, this is the reachable set. Okay, so if you can make sure this RT is safe, then this basically means the system is safe, right? So this is the classical definition. So we started with this, but then quickly we realized this is not suitable for stochastic system. The reason is being exactly that the stochastic disturbance are unbounded. You can imagine a very simple system, which is basically means your state is a Gaussian noise. You can imagine what is a Gaussian distribution. Everyone knows it's going to look like this, right? So the special property is about Gaussian distribution is it can take any possible values. Okay, so if you use this classical definition, quickly you would realize that the reachable set is just the entire state space, and that's not very useful to you because clearly you say, okay, this is not safe, right? So we have to kind of modify this definition. And this is the definition we use, and that is also the definition used in the literatures. So we just need to make some small modifications. We have some initial set. Well, again, because we consider both deterministic and stochastic disturbance, so we consider we also have some deterministic disturbance, doesn't matter. The major modification is we introduce a number here, which is between 0 and 1. That's like your confidence level. Okay, we will see what this means. Then we say that you have a set at a one-time instance. It's called the delta probabilistic reachable set for certain dynamic system we consider. Okay, at the time t, if for any initial condition and any disturbance, deterministic disturbance, like then After you fix these two, the trajectory still is going to be stochastic. Then the set has to satisfy such that the xt belongs to this set with high probability. It's okay that with certain probability you can go outside because that's the nature of stochastic system. As long as you make sure that you stay inside with, let's say, probability 1 minus 10 to the power minus 6, you should be okay, right? I would be willing to take a AV that if it can guarantee this level of safety. So this is what this means. Okay, typically delta has to be relatively small to ensure safety. Okay, so this is the modification. Okay, so how do we? So the question is, how do we approximate this delta probabilistic reachable set? The most, if you have a supercomputer can do everything, there's one golden solution is Monte Carlo. You simulate everything. You simulate 1 billion, 10 billion trajectories. If you can make sure everything, almost everything there, stay in the set, then this gives you roughly the approximation of the reachable set. But that is in the ideal world. In real life, you have computational budget, okay, and there are many other constraints. You just cannot do this. So is there any better way to do this that is computationally efficient? Okay, so that's what we are doing. We realize that we can do some decomposition. This is the main strategy we are using. We call this a separation strategy. And eventually essentially what we are doing is we reduce the problem into a deterministic problem. So there's a fundamental principle here is for the same problem, the reachability analysis, the deterministic problem is much easier than the stochastic problem in terms of computation, okay? So it's very tempting to reduce a stochastic problem into a deterministic problem. That's exactly what we're doing. So to do this, we introduce some called the associated trajectory. It's basically some coupling. So for every trajectory you have for the stochastic system, I'm going to introduce a nominal trajectory, which is the trajectory of the deterministic system, which is this one. And you see the only difference between this one and this one is this has an additional stochastic disturbance. So if you simulate this, what you can imagine is the stochastic one is going to fluctuate around the deterministic trajectory, okay? So what I mean is the probability for the stochastic trajectory and deterministic trajectory to be close to each other is relatively high, okay? If you know this, okay, then what we can do is we just need to compute the reachability set for the deterministic system, and now we know the stochastic system is not going to be too far away from your deterministic system, so I know I just need to make the reachable set a little bit larger, then this is going to be my probabilistic reachable set. So this is the formal principle here. So what we do is we just need to compute a reachable set for the deterministic system, which we can adopt many algorithms. Some of the algorithms are developed here in CU Boulder. And then what we need to do is we try to find a radius, which is the distance, such that this condition is true. So the probability for this two value to be less than this is greater, is large enough. Then you can quickly say that if I put these two together, then this is going to be a delta probabilistic reachable set. So this is basically what it looks like. So you use this to model this is just to model the reachable set for the deterministic system. And if I know they are close to each other with this radius, I just need to put this ball and this together, take the summation in a certain way, then I get a larger set. And this set is going to be the delta probabilistic reachable set for the stochastic system. And this result is relatively easy to show. But this is the basic principle. So once we adopt this strategy, the problem reduced to what? So because eventually what we really need is we still want to make sure this set is as small as possible, because that the tighter you get this bound, the better the safety verification result you can get. So Therefore, what we need is you want to make sure you find a very small radius to capture the difference between the stochastic trajectory and the deterministic trajectory. So this is the problem. After this separation strategy, we get this problem. So we would like to find as small as possible radius r delta t, which would depends on t. It also depends on delta, which is your confidence level, such that the distance between these two states is satisfy this assumption. Okay, so that's the problem. So with this separation strategy, we reduce the reachability analysis problem into this problem, how to quantify the distance between stochastic trajectory and deterministic trajectory. So how do we do this? How do we quantify the distance between two trajectories? So if these two trajectories happen to be both deterministic, there's a big body of literature already in the control community. It's called contraction theory. Okay, so it's something like this. It's some property of a system. So I would quickly go through this. It's basically, this is certain, if you don't understand this condition, it's fine. It's kind of certain Lipschitz continuity equation, continuity condition. It's basically some condition that most system hold would has. Okay, so if this system satisfies this assumption, which these two are equivalent conditions for this, so let's not worry about the detail, but it's just one assumption on your dynamic system. Okay, if your dynamic system satisfies this assumption, then you can actually quantify the distance between these two trajectories of these two different trajectories of the system, and their distance is going to be bounded by this value. And especially when C, this value here, coefficient is less than 0, people call this contractive system. And you see if C is less than 0, then the system behavior would have this. So basically means their distance is going to shrink exponentially fast. So that's a nice property. But even if C is greater than 0, you get a bound to quantify the distance between the two. So the way they show this is just use a quadratic Lyapunov function and do some calculation. You get this. Okay, so that is what the people use to quantify the distance between two deterministic trajectories. So can we do this for stochastic trajectory, like for our purpose? Well, it turns out you can. So it's actually the result is very similar. So here, this is the system we consider. This is our stochastic system. We can assume the system satisfies this contractive condition. But in addition, we assume the coefficient, so the energy of the disturbance is finite, is a very standard assumption. Then you can again use a quadratic function as a Lyapunov and you do some calculation, you get this final result. You get that the expected value between xt minus xt quadratic term has to be less than this. Okay? So the reason I take expectation is because things are random now, so I had to do some expectation to do this. Okay, so that is what you get. But this is not what we want. What we want is we want to say the probability of this value less than certain value is large enough, right? So if you want to translate this type of this moment condition into this probabilistic argument, you can use something called the Markov inequality or Chebyshev inequality, what you learned in the probability course. So basically, once you have this condition, you can argue that the probability of the distance between these two states less than this value here is greater than 1 minus delta. Okay, so this is a classic. This is more like 15 years old. Okay, that's good. But is this the best we can do? Now, is this the best we can do? If this is the best we can do, then it's fine. But is this the best we can do? Okay, so typically, to answer this question, what we did is we try to verify if this is, you can improve this result in linear setting, right? If you cannot improve this result in linear setting, then this means the best you can do. So this is what we get using this approach. This is what you get. Let's see what we can get for linear setting. So for linear setting, we consider, let's say, the simplest linear system, which satisfies the same assumption. So this is my linear stochastic system. This is the deterministic counterpart. Okay. if we can apply the result on the previous page to this system, you get this result. This is the basically applied the result here. You get this, okay? But for linear system, there's something really nice is everything is Gaussian, okay? So which basically means xt is a Gaussian random variable where the mean is really lowercase xt, and the covariance in this special case you can actually compute. So what's so nice about Gaussian distribution? Gaussian distribution decays extremely fast. So there's something called the Gaussian concentration. So basically, because if you have a Gaussian random variable whose covariance is this, you can actually say that the probability of this distance to be less than this value here is greater than 1 minus theta. Okay, let's take a look at the difference. Okay.
But that's cheating, right? You're saying Markov inequality is much weaker than Gaussian concentration, which we know, right? Markov inequalities are weak, right?
Yeah, no, I'm not. I'm just trying to say the nonlinear result obtained previously was not good. Yeah, that's yeah, we are going to fix this problem. But yes, exactly. So I just want to tell the difference between the two. So this is based on the Markov inequality on the previous page. And this is what you get for the linear system. I mean, under the same assumptions. So what we want this is the radius. We want this quantity here to be small, because if this radius is large, the result is going to be conservative. We want to make sure this is as small as possible. So this is what we got from the previous literature. This is what you can get for linear system. So if you, let's say, take one instance in some aerospace application, you need the delta to be 10 to the power minus 10. That is the level of safety you need. Then you can plug this delta into these values. Then for this value, you would get 10 to the power 5. For the Gaussian case, linear system is about 5. So there's a huge gap between the two. So which means for safety critical applications with this small delta, this one is actually not very useful in comparison to the Gaussian setting. So this means at least the previous result is not tied for linear setting. Okay, it's possible it's tied for nonlinear setting. We didn't know at that time, but we answered this question. What we did is we showed that you can obtain exactly the same bound for nonlinear system. That's the main contribution for the first part of the talk. Okay, so we basically show this is true for nonlinear system. I'm going to use a few slides to explain how we did this. Okay. Okay. So that's the current stage. Okay. So how do we do that? Where this result is really nice, it relies on what the linear property. Everything is Gaussian. But whenever you have nonlinear thing, nothing is Gaussian. Clearly, you cannot use Gaussian distribution. So what's the next best thing other than Gaussian? Sub-Gaussian. Okay, sub-Gaussian. What is a sub-Gaussian? It's a generalization of Gaussian random distribution, but it's include much larger class of distribution. So this is the formal definition for the vector case. You have a random vector is sub-Gaussian with some variance like theta square. If this what we call moment generating function is bounded above by this value for any lambda, and for any this L is just a unit vector in any directions. So this here is the inner product. So this is the standard definition of a moment generating function. It says it's a special property of a distribution. And for Gaussian distribution, this theta is just a variance. So it's a strict, it's the most natural generalization of a Gaussian distribution. What's so nice about sub-Gaussian distributions is that it shares exactly the same concentration as Gaussian. So whatever you can do for Gaussian, you can do the same things for sub-Gaussian, at least if you want to bound the norm of it. Okay, so this is what this result is about. We can actually generalize this slightly. So basically is if you have a sub-Gaussian random variable, then you can say that the probability for this norm to be less than this value here is greater than at least 1 minus theta. And there's some hyperparameter epsilon 1, epsilon 2, but just means they are a set of coefficients. It's not a unique one. You have a set of concentration inequality. But for us, we can just view this as a constant, epsilon 1, epsilon 2. It doesn't matter. The most important thing is this bond here depends on the system dimension as a square root of n, and it depends on the confidence level as a square root of log 1 over delta. So this is exactly the same for the Gaussian distribution. This is good. So this means what? If we can show the difference between if we can show xt minus xt is sub-Gaussian, we are good to go. That is what we thought. We couldn't do it. The truth is this is not sub-Gaussian, okay? So we couldn't do it. It's not sub-Gaussian, at least in the strict sense. So we have to fix this. So the secret ingredient of this line of research is a very intriguing mathematical tool we discovered called the average moment generating function, which I think is really, really powerful, okay? This is our first application of this method. But this is so the moment generating function is just this. What is the average moment generating function? You just average over the vector, yeah? So the moment generating function means for every vector, yeah, this guy, the expected value of this e to the power thing, is bounded. That's probably too much to ask. So it turns out you don't need this. You just need to make sure the average of this moment generating function over the unit sphere is bounded. Then you can get exactly the same concentration inequality. Okay, it's basically, you can view this as a relaxation of the sub-Gaussian definition, but it's much easier to achieve. So this is this result discovered in 22 in a different community. They realized that if your average moment generating function is bounded above by this, which is like a relaxation of the definition of sub-Gaussian, then you can argue the norm of x satisfies exactly the same concentration, exactly the same. There's no difference, okay? But this is a much relaxed condition. And what we did is we managed to show that we can actually bound this quantity along our system dynamics under certain assumptions. And that is how we show what we want, okay? So this is the average moment generating function. So with the help of this average moment generating function, this is what we get. We show that with probability at least 1 minus delta, the distance between these two is less than equal to this with high probability. And this is exactly as the same as the Gaussian case and with this dependence. And I'm going to skip the proof. If you're interested in this, take a look at the paper. It's once you accept the definition of average moment generating function, it's actually quite easy to follow. That's what we get. So basically what we have is we managed to establish a result that is as good as the linear setting, okay? And this is just to show you how tight is this result in comparison to Monte Carlo. So this is what you get from Monte Carlo. This is our bound. So roughly saying that that's it, okay? It's more or less the same as the real thing, what happens under the same assumptions, okay? If you have a specific system, of course, you may do better. But if you allow the system to be any system in the same function class, then that's the best you can do, okay? And with this result, I would like to present a general recipe for probabilistic reachability analysis for stochastic system. So what you do is, if you have a stochastic system like this, what you do is you first find a reachable set for this deterministic system. You can use whatever method you prefer, okay? Then you just need to combine this with the ball we compute, whose radius is this. Then that gives you a very good approximation of the reachable set for the probabilistic system, for the stochastic system, okay? That's the first part of the talk. Any questions?
So I wasn't clear how you managed to bound, under what conditions you bounded the average moment generating function?
The only assumption we made is this. Okay, sorry. So the question is, I think the question is, how do we get our main result? How do we, okay, so the question is, how do we establish our main result? So the answer is this is an application of this inequality over here. So basically what you need to do is to bound the average moment generating function. And it turns out that what you can get is you can basically, what we did is we use the average moment generating function as a Lyapunov function. You propagate this along the system dynamics, you realize you can control it. This is actually written in this line, but it's very dense. Yeah. So basically it's the standard moment generating function, you cannot control the evolution, but after you take the average, we found a way to bound this evolution under the assumption. And the assumption we have is just a very typical, basically is the deterministic part is contractive and the stochastic part determines the disturbance has finite energy. Both are reasonable, yeah.
So follow that here you're using like an actual VP, right? An actual supermartingales.
Yeah.
Like argument to prove contraction.
It's
synthesize that on a system.
Yes.
The basis to get like better contraction result. Have you tried that, or is that?
That's not here. What we did is we assume we have this assumption. Then we construct a specific Lyapunov function to achieve what we want. Okay. The Lyapunov function we have is not so flexible. It's not like we can change this very much. But there is one generalization here is that here we use 2-no, but you can easily extend this to weighted 2-no. So recently we managed to do this for the manifold, Riemannian manifold, but that's a different story. But there are certain level of generalization you can do, but we don't have to. So actually the important thing here is we don't solve optimization problem to synthesize this. We construct this analytically as long as you can compute this C and the sigma, which could be another question. So we don't claim we solve this part. Actually, we realize this part is not that easy, okay, in our practice. Yeah. Yeah.
Assumptions about the system itself.
Yes.
Assumptions kind of limiting scope where the helps can be applied within standard interface assumptions.
This assumption holds for any nonlinear system. The only tricky thing is that the C and the sigma value can be large. So which means when this C and the sigma get large enough at a certain level, the result is not going to be very useful. Yeah. Yes. Yes.
In the system to get it.
Contractive. Yeah. Every system is contractive because we don't consider the strict sense of contractive. It's even if it's an expansion, we call this contractive with some positive coefficient. So the bottom line is every system satisfies our assumption. It's just the coefficient can be, there's a hyperparameter there can be bad that eventually is not going to be very useful. Yeah. Definitely, that's an ongoing research. I think I need to talk to more expert on this domain. Yeah. Repeat the. Okay, sorry, I will try to. Yeah. Do you have?
So on the evaluation, I think you said you converted Monte Carlo.
Right? Yes.
So did you try like more accurate methods, like was it Monte Carlo, was it still better, or?
It's not a comparison to show which, sorry, your question is on this page, we compare this with Monte Carlo. Which one is better? Okay. We cannot beat Monte Carlo. Monte Carlo is the golden standard. Monte Carlo always gives you the best result if you have an infinite budget. Okay, we just use this as the golden standard to show that we can achieve comparable result, but with negligible computation. Yeah, yeah. You cannot beat Monte Carlo if there's a supercomputer there. Yeah. Okay. Okay. That's conclude the first part of the talk. How much time do I have? 10 minutes? Oh, that's wonderful. I really want to get to the second part. Okay, even let's say 10 minutes. Let me try. Okay, so we have this result for probabilistic reachable set. Okay, now we want to use this for safety verification. Initially, we thought, that's it, we can do it. But we realize there's a gap. What is the gap? Okay, so just imagine this scenario, you have a zone, you have some obstacle, okay, you have some controller, let's just do the verification. Then due to disturbance, the zone can take a different trajectory. So all these are possibilities. Okay, so if you just think about this, if I want to make sure this system is safe with high probability, what you really want is you want to make sure the probability for this trajectory to hit this obstacle with very small probability. Okay, in the first part of the talk, what we establish is that given any time instance, the probability of this within a certain set is high enough. But if you want to apply this to the trajectory level, you basically have to apply this to every time instance. And there's some probabilistic argument that will tell you that quickly is going to get really, really bad, and it's not applicable to continuous trajectory. Okay, so what we got in the first part of the talk cannot be used to verify the continuous stochastic trajectory safety. Okay, there's a gap because the result we obtained is for every fixed time instance, what we can say. Okay, how do we bridge the gap? So there's only one type of result I'm aware of that can do such things. This is called the martingale inequality. I think many of you use this in your research. So, and this is a very interesting inequality I want to explain. What is a martingale? It's a random process which satisfies certain property. So here, you can imagine this MT is a stochastic process. It satisfies certain property. This property basically means given the current value, let's say, given the current value S, the expected value of MT in the future is going to be less than equal to my current value. This is what you do in gambling, actually. You have some money there, you want to do gamble. If it's a fair game, you can expect the money you get in the future at some point, it's for sure going to be less and less if you are doing random guess, okay? Then this is the martingale type of definition. Then there's a very famous inequality called the martingale inequality, which tells you if this is the really what's happening in practice, then the probability for the maximum value of MT greater than C has to be less than equal to the initial value divided by C. Okay, so that's a very important result. So what does this tell you? Just let me use the gambling example again. You have some money, you go to Las Vegas, you do some gambling. Okay, you are playing the slot machine, a very fair game. So it satisfies this assumption. You invest, let's say, $100. Then you tell yourself, I want to make 10K today. This inequality tells you if it's possible for you to make 10K, the probability for you to reach there, so this is 10K, the initial value is 100. So you know it's less than 1%. Okay, and that is what the math can tell you. So gambling is risky, okay? And for us, this is what I want to emphasize is this is the trajectory level guarantee. So it doesn't matter when this happens. So it's basically the maximum value of MT greater than this is less than this. Okay, so this is just if you have a random walk, this basically if this is the upper bound, so this inequality captures the value of this stochastic process across this boundary. Okay. So almost all the results that hold for continuous time trajectory use this result. That's the fundamental thing here. So this is the fundamental foundation of a large group of research called the stochastic barrier function. Okay, so there are many things also going on here at CU Boulder. So we are not doing exactly the same thing. One thing we realized that is this, if you want to use this type of research like stochastic barrier function, you have to design a martingale, and this typically is very difficult. Okay, so instead what we did is we just say, okay, let's just construct a martingale that is enough for us. And we made it, okay? So this is, again, the separation strategy. So we are not, what we do is, this is the extension of the separation strategy. So on the previous, in the first part of the talk, right, we say that if we can quantify the difference between xt and xt at a one-time instance, then we can do something about the stochastic system. But if you want to verify the trajectory level, you have to make this result into what we call probabilistic tube. So basically is that if this black line is your deterministic trajectory, you want to build a tube around this. This is a spatial temporal tube, so that if your trajectory stays in this tube with high probability, okay, then you can do something to the safe set so that so let's say I want to make sure that this zone is safe with this obstacle. Once you have this tube, what you can do is you can shrink the safe set of the original system a little bit, so you have a smaller safe set. And if you can verify the deterministic trajectory is safe in the smaller safe set, then you can guarantee the safety for the stochastic system. So it's the same idea, but the difference is now you want to have the trajectory level tube instead of one-time difference. So this is the problem we are going to solve. Given a time horizon, you want to establish a very small probabilistic tube, which looks like this, such that the stochastic trajectory stays in the tube. So this tube, I think, yeah, this is the tube. Okay, so I wouldn't have time to go over the math, but the thing we use is we modify the definition of a martingale slightly. So we introduce something called as alpha martingale, which has been studied in certain degree, not exactly, but you just view this as a generalization of martingale. And the more interesting part is that we show the average moment generating function we use in the first part of the talk, it is a alpha martingale. So with this, we establish our result, which is this one. That's what one thing I'm really proud of. So what you can establish is under the same assumption in the first page, let me finish this. The trajectory difference, so which means the difference between the two for any t is small enough with high probability, and we can quantify this radius. And this radius is very small, is the smallest you can get. And this is the simulation. So this is one, I think this is one stochastic process, and this is the Monte Carlo, and this is the bound we get. So we can say that our bound is very close to the Monte Carlo, and this is another stochastic process. This is the bound we get, this is the Monte Carlo. So it's basically almost aligned with the Monte Carlo result, but you can compute this in closed form. Sorry.
So fine martingale, it's just a martingale, like there's a different martingale, right? With e to the power a.
Yes, exactly. Yeah, so the question is, what are the new things about this alpha martingale? It's this alpha martingale is just a linear, kind of a linear transformation of the martingale. But just for this specific one, it turns out this has not been defined before, so we just introduced this definition. But you just say one generalization of martingale. It's not a big deal. Yeah. But we really need this alpha martingale to establish our result. Yeah. Okay. So this is the most important result I would say in this part. Let me just try to show here. This radius, we want to make sure this radius is very small, as small as possible. You see the radius again grows as the delta as the square root of log 1 over delta, which means it's the best you can get. And also it scales as the total time horizon as a log t, which means you can apply this to very large system. And also it scales as the square root of n, which means you can apply this to high dimensional system. Okay. And it's tight, which means you cannot improve this. Okay, so with this, I want to present our general recipe for safety verification for stochastic system. So what you do is you have a stochastic system and you have a safe set. You want to make sure that this stochastic system is safe with respect to this safe set with high probability. What you do is you make the safe set smaller. So you just take a portion out where this B is, this ball has the radius we can compute. Then if you can show the deterministic system is safe over this smaller safe set, you can conclude the stochastic system is safe for the original safe set with high probability. And typically you can go up to 10 to the power minus 10, 10 to the power minus 20. So as much as you want. Okay, so that's our general recipe. And finally, let me quickly go through a few numeric examples. So this is how you use it. So let's say this is verification. So you have a system, stochastic system. Okay, you have a few obstacles. You want to make sure this vehicle doesn't hit the obstacle. Okay, it's a stochastic. So what you do is you make the safe set smaller, which basically means you make the obstacle larger. Okay, and then if you can verify the deterministic part, you see it's very smooth. It doesn't hit this larger obstacle. Then you can make sure the stochastic system doesn't hit this original obstacle with high probability. Okay, actually this type of approach is commonly used in practice. So the main thing here is how do you quantify the buffer? Okay, this is how you use for safety verification. You can do more fancy things, like you can apply this to handle more complicated tasks specified, for instance, by temporal logic. So here, what we want to say is we want to make sure the stochastic system should avoid this obstacle, eventually would reach this area, but you have to go through the blue area first. So what you do is you make this obstacle larger, you make these two areas smaller. If you verify the deterministic system would satisfy this stricter STL condition, then you can make sure the original system satisfies this STL condition with high probability. And very recently, we managed to apply this to control synthesis, so which is beyond verification. You can design certain stochastic MPC method to make sure that the system follows your safety criteria. So, but I'm going to skip that. So this is the takeaway. So what we present is a scalable method for safety assurance for stochastic system. I think the most important message could be here. What we did here is we use certain technique to reduce a complicated stochastic problem into an easier or more scalable deterministic problem. Then you can use the method there to solve the problem. So that is the general philosophy in this approach. And in addition to this, what we present can be just another tool to analyze the stochastic system. That's a different bonus. And this, if you are interested in this line of research, these are a list of publications we got recently. And the first two are what we present, but there are several others which are also quite interesting. And with that, I would like to conclude. I would like to thank my collaborator again and also my sponsors. Thanks. Yeah.
More question? Yeah,
Thanks for the talk. My question was, in all your utility analysis, you care about finite time horizon, right?
Mm-hmm.
So what's the longest time horizon you consider?
So the question is, when you do verification task, there's a capital T here. Okay. So if you want to do verification, the T should be large. What's the longest T? We have tried. I don't know. I need to ask my student. But What I can say is this our result has a very nice dependence on t. It's a square root log t. You can imagine that you can make t really, really long. Definitely much longer than existing work. Cannot make t infinity, but t can be large enough. Yes. Enough for many applications. Yeah.
More question? Yeah. So I guess it's the critical part of this method is to find good bounds for small c and sigma, right?
Yeah.
And those are local bounds. In other words, you're finding those bounds for all x and t. Are you assuming that you're restricting your system to some compact set? Otherwise, those bounds may not exist. Right?
Yeah, that's a good question. So the key, so let's get back to the definition. Yeah, so let's repeat the question. So the question is, our result depends on the assumption that this system satisfies these two assumptions, and you have a certain way to make sure. So our result depends on these two parameters, okay? And also our result requires these two parameters, or our result is not going to be good if these two parameters are large, okay? How do we make sure we can get a very good estimation of this C and sigma, okay? This global coefficient. In this talk, yes, we assume this C and sigma are global coefficient. You can make with some probabilistic argument, you can make this into a local, not that local. You can say that as long as C and sigma is less than a certain value in a compact set, and you stay, and then you have a recursive argument to show you stay in this compact set with high probability, you're good enough, okay? Or even more recently, we can do is we can make C and sigma time dependent, even spatial dependent. So this can greatly relax these assumptions, but that would add some additional computation burden. Yeah, that's there's a trade-off. Yeah, sometimes for certain system, that is actually an obstacle we face that it's actually not that easy to have a good C. And typically, this system we assume we have another controller already applied to the system so that to achieve certain C. But even that is not a simple task. Yeah.
Another way of interpreting this is to just say that you can handle a whole class of drifts in your SDE.
Yeah.
Any function G that satisfies
yes.
to some sigma level is allowed, right? And that makes the bug into a feature.
Yeah. And what?
Like you're basically saying like you can handle any G that satisfies that sigma.
Yes.
That's not part of your argument.
Yeah. I mean, we present a framework. How you can apply this framework effectively in practice? It depends on how fast you can or how good are these coefficients you can get in your practice. So that is something we didn't get into. Yeah, we admit this is one engineering difficulty of applying this framework. Yeah.
Yep. This is the last question.
Okay, so very interesting work.
Thanks.
And, thank you. So constructing a tube,
yes.
Interesting in this classical method. I'm wondering if it's possible to extend this method to beyond tubes, because what the tube does is essentially shows you that within the tube you're safe. There's a probability of going outside the tube, right? You're unsafe. What if instead every time instance I can give you the probability of unsafe, right? And constructing a tube, I just say at this time step you're unsafe with this probability. At this time step you're unsafe with this probability. Can you extend that point-wise probability to probability of the entire trajectory?
So the question is it's actually quite a tricky question. So the question is, how do I repeat this question? So the question is that okay. So let me interpret this in another way. So in the first part of the talk, we established the result, which is guaranteed at a one-time instance. In the second part of the talk, we get the result for the entire trajectory, so which is the tube. The first part is you have one-time slice, what do you get? So how do we bridge the two? if you get a sequence of results for the first part, can we build this for the second part? That's a great question. I hope this is what you ask. And yes, you see, if I omit the detail, this second part is how we get the result. We did exactly this. So the first part of the result hold for any C, but we realize it's not good for C less than 0. So for real contractive system, what we did is we apply the first part of the talk, the result for many time instance with the step size to be delta t. And for everything in between, we use this type of result. Then we put them together. That's what we got here. Yes. So that quick answer, yes, there are certain ways of combining them. But there are definitely some restriction. So far we can only do tube, which is basically means disk or ellipsoid. We cannot do other norms other than weighted 2 norm. So there's a limitation over there. But there's certain things we can do and we cannot do. Yeah.
Okay. Let's thank the speaker then.
Thanks.
So it's gonna stay a few more